purpose of this lab is to find the mass of the black hole by analyzing a star's motion and determine the initial velocity the ship must have when it leaves the surface of the planet to avoid crashing on the planet or in the black hole. Some of the fundamental physical principles include Newton's second law and Newton's law of universal gravitation. Newton's law of universal gravitation is the attractive non-constant force between two objects with mass. The gravitational force is equal to g times the mass of the system times the mass of the source divided by the distance squared times negative displacement unit vector. Capital G is just the gravitational constant shown on the slide, and the distance is just the magnitude of the displacement vector, position of the system minus position of the source. Fnet is equal to the change in momentum or the change in time. Fnet is also equal to the parallel forces plus the perpendicular forces. The parallel component represents the changes in the magnitude of momentum, and the perpendicular component represents the changes in direction of the momentum. This means the parallel component is equal to p hat times the change in magnitude of momentum over the change in time, and the perpendicular component is equal to the magnitude of p times the change in p hat over the change in time. We'll also be utilizing the position update formula and the velocity update formula. Since the gravitational force is non-constant, V average in the position formula is V final. In part 1 of the experiment in finding the mass of the black hole, we assume that net force on the star is solely due to the black hole located at the origin. The magnitude of Fnet is equal to the magnitude of the gravitational force exerted on the star by the black hole. Rearranging the equation, the mass of the black hole is equal to delta P times r squared divided by delta T times gm, which is equal to Fnet times r squared over gm. In part 2, there's a planet orbiting the black hole and the spaceship on the planet that has to take off without crashing on the planet or the black hole. From the results in part 1, we can determine the initial velocity the spaceship must have when it leaves the planet to avoid crashing. I also want to know a general assumption for both parts is that the black hole is at the origin, so when getting the displacement vector to find r, it's just the magnitude of the system's position. In the results, the mass of the black hole is 1.083 e 34 kilograms, and the initial velocity is negative 4 e7 2 e6 0 meters per second. In part 1 of the experiment, the system is the star and the surroundings is the black hole. To set the initial conditions, we need to edit the mass of the star and the time interval between data points. The gravitational constant is already set to be 6.7 e negative 11, the mass of the star is given to us to be 2 e 30 kilograms, and delta t is 86,400 seconds since we're assuming that the time between data points is 1 day. To get the mass of the black hole, we need to know Fnet. To find Fnet, we need to compute P initial and P final to get delta P. Because momentum is equal to mass times velocity, P initial is equal to the star's mass times the initial velocity, and P final is equal to the star's mass times the final velocity. Now we can set delta P equal to P final minus P initial and make Fnet defined as delta P over delta T in the code. With Fnet defined, the mass of the black hole is equal to the magnitude of Fnet times the magnitude of the star's position squared over g times the mass of the star. For the parallel component of Fnet, we just need to incorporate the formula into the code. P hat is just the P initial divided by the magnitude of P initial, and the change in magnitude of P is the magnitude of P final minus the magnitude of P initial. As for Fnet perpendicular, it's equal to Fnet minus the parallel component. In our results for part 1, the mass of the black hole is found to be 1.083 times 10 to the 34 kilograms. I've also listed the magnitudes of Fnet, Fnet parallel, and Fnet perpendicular that we got from the code. Now for our discussion question for part 1. What does it mean? According to Newton's second law, the change in momentum over the change in time is equal to the net force. This means that the net force and its parallel and perpendicular components are the same as the rate of change of momentum and its parallel and perpendicular components. We can see this in the momentum principle formula and see how it applies throughout our code. Moving on to part 2, in our initial conditions, we can set the mass of the black hole from the results in part 1. The other constants like g and the mass of the planet and the ship are already set. As for the initial conditions for the planet, it's already been set and doesn't need to be edited. However, the initial conditions for the spaceship has not been set yet. After we finish writing the code in the calculation loop, we can edit the values to find what the spaceship's initial velocity needs to be to avoid crashing. To find the net force on the planet, we need to find the gravitational force on the planet exerted by the black hole and the gravitational force exerted on the planet by the spaceship. To find these gravitational forces, we just need to implement the formula. With these gravitational forces, Fnet is equal to the sum of them because Fnet is the sum of all forces exerted onto the system. In this case, the system is the planet and the surroundings is the spaceship and the black hole. To find the net force on the spaceship, we follow the same process except the system this time is the spaceship and the surroundings is the planet and the black hole. With the net force of the planet and the spaceship defined, we can code the motion of the planet and the spaceship using the position update formula and the velocity update formula. Now that we've finished writing the code, we can set the shift speed in the x and y direction to different values and see what the shift's velocity must be to avoid crashing. By guessing and running different values through the code, I found the spaceship's initial velocity to be negative 4 times 10 to the 7, 2 times 10 to the negative 6, 0 meters per second. What if I wanted the spaceship to be in orbit around the black hole? So adjusting the initial velocity to be negative 1 e6, 8.6 e6, 0 meters per second, this was the closest I could get for the spaceship to go into orbit. Since this lab is entirely in GlowScript, possible sources of error mainly come from human error. I could have made a mistake in typing the code and putting in the wrong formulas. I also could have set the initial conditions improperly, making the results inaccurate. So what can we conclude from this experiment? Just by coding, I can create a computer simulation of a black hole and see how it can affect the motion of a planet or a spaceship, and observe the force of the black hole acting upon different systems.